So these are the things that I will like to discuss in the rest of the class. So there are many vulnerabilities in the flow. Okay. See, today we are integrating IP, right? We are integrating a lot of IP. I already mentioned that. So in such an IP based design flow, there may be some vulnerabilities in the design and verification stage, in the synthesis, parasitic extraction, STA phase, in the manufacturing and packaging phase, and finally in the validation or test phase. So what can happen here is, not only are we adopting to a IP based design flow, we are also outsourcing a lot of our activities to other people, right? And most of our chips also have wireless connectivity. So data is easier to steal today than it was once upon a time, right? So there are some different angles that we have to. So people are using, hacking to try and get the data of your chip. Okay, and unfortunately, test and debug are two places where hackers are most active. Okay, you take your scan chains, right? Most people are not aware of what the scan chains are, right? That is only for people who are in the test to know. The PCB designer really doesn't know that there are scan chains and they are used in test, etc. We don't know that. Similarly, scan chains can be used for debugging, right? A boundary scan can be used for debugging. Now, if you can read the content of a register and pass it on, right? How hard is it for you to read, let us say, a password stored in some memory, right? So, test and debug architecture can be misused to steal information from a chip. Then people are beginning to use things like Trojans. Okay, what is a Trojan? So, if you have a chip, you can insert a small hardware module called as a Trojan, which wakes up after many, maybe months or whatever. It has been programmed to maybe steal information and keep it ready. See, it's part of the chip, so it is aware of all the activities that are happening on the chip. So it may be, copying information from the chip, etc. And at some stage, it is ready to send it to some external party. See, remember, wireless connectivity is now available. Similarly, it may cause some damage, right? There are some attacks that are possible using which you can, cause a lot of problems in the chip, right? It can start dissipating too much power and it can cause the system to fail. So there are many adverse effects that Trojan can produce. Okay. Similarly, I already mentioned that you can produce fake ICs. In the same way, we are beginning to outsource, right? See, even the fabrication is being outsourced. See, many companies are now fabless. They depend on an external fab in some other country to make those chips and provide them back. Now, when making these chips, if the order is for, let us say, 10 million, What prevents this company from manufacturing another 2 million? They will invest in making these additional 2 million. Okay, and they will bring that into the market under a different name. Okay, everybody thinks that it is a product that somebody else designed, but actually it's nothing but a stolen design. Similarly, as I mentioned to you earlier, some used ICs recovered from e-waste can be brought back to the. So this can also be a problem. And we also talked about side channel attacks already. That is using scan chains to steal data. Those are called side channel attacks. The vulnerabilities are not acceptable in markets like automotive, biomedical, okay, or industrial, defense. So these are all places where we are worried about. Okay. We talk about industry 4.0, right? We talk about automotives which are self-driven, and today semiconductors are being used in so many places. Okay, so in a number of these places, such vulnerabilities will cause a lot of problems. So testing is becoming more important than ever, right? If, for example, there is some data on recalls of cars. Okay, so over 3 lakh vehicles were recalled in, let us say, I think this was 2020. Now, why? Because there are bugs left. Okay, it could be a software bug, or it could be a hardware problem. It gets discovered when the user is using the vehicle, right? Imagine that without having pressed the accelerator, the car is speeding. Okay, it can be a very sort of a scary situation. It has happened. Right? So people are worried about these recalls, and there is some data on why these cars are being recalled. There are many reasons. It can be a very simple thing like maybe a wheel cap was painted with wrong color. For this also they may recall. Or maybe the switches have very sharp edges and some people are getting some small injuries and they complain. So that also may cause a recall. This is more serious, right? In the event of an accident, the safety belt, we advise everybody to wear safety belts. But suppose the safety belt is not able to, the person is not able to release the safety belt, it is stuck. This is more of a mechanical problem, possibly. Even then, it will be recalled. Or here, maybe there is an electric vehicle and maybe it can catch fire. So, these are all hard, these are more dangerous. So, the car manufacturers are now beginning to use a lot of electronics, and earlier they were using more of mechanical engineering, right? For example, the famous IC engine, internal combustion engine. This is a mechanical engine, whereas today people have moved to EV, electric vehicles. So they depend on manufacturers of electronics to ensure that these things don't happen. Okay, and if you have to guarantee that, then your costs will go. Okay, they will go up. So verification and test, their roles have changed over a period of time. Okay. In addition to just functional verification, they also have to provide quality protection. So there is a whole term called quality protection as a service. Similarly, they have to worry about functional safety. What is functional safety? If there is a problem because of aging, etc., the hardware goes into a safe state. Similarly, ensuring reliability of the components, ensuring that the security of the component is maintained. And when if a failure occurs, what is the root cause? All these are now becoming part of verification and test. Okay. So that is the reason why. So you can see this picture. The auto manufacturer typically buys. See, they don't directly buy ICs. Okay, ICs are made by electronics companies. Similarly, components like resistors, capacitors, there are companies that source them, and there may be other companies which provide simpler ICs like this, right? Now the card manufacturers, there are people who build cards meaning systems. So there may be people who assemble these things, build a, maybe it is meant for infotainment, maybe it is meant for GPS tracking. So people build these cards, and the car manufacturers buys them from these guys. Okay? And the car manufacturer will put some pressure on these guys to make sure that they have done adequate testing, functional safety, reliability, etc. And these guys in turn put the pressure back on the companies that make these ICs. So you should understand how testing occurs. I think I have mentioned this in an earlier class. First, they do what is called as wafer acceptance test. See, it may be possible to reject an entire wafer by examining the wafer. Okay. So we insert the wafer in what is called as a chuck. Okay. And there may be many dies on this wafer. So all this is done by a robot. Okay. So taking the wafer and putting it in a chuck and moving that wafer, etc. So there is a robotic arm that contains these probes. Okay, that probe will come and make a contact with the die. Okay, and it can apply signals, make measurements, etc. So the movement of the wafer, the chuck will possibly not move, it will stay in one place. The wafer will move, and that is done by the robot. Okay, and the kind of tests that they do on the wafer are simple tests like are digital pins connected or not. Electrical connectivity. power is connected or not, ground is connected or not. So any gross failures, they will reject and they'll ink the wafer saying this is a bad IC. Here is another bad IC, here is another bad IC, etc. The dies which did not fail at wafer probing, they are packaged and they are tested. And you should see what kind of testing should be done, okay? Because the modern ICs have so many different failure mechanisms. They are doing a lot of different kinds of tests: stuck at fault test, transition delay fault test, then bridge fault test, functional tests, uh, use test compression. All these are memory based. So here I have shown the breakup. Okay. So this memory test patterns perhaps are a major portion of the test that we apply. Makes sense because a lot of our chip area is occupied by memories. Then voltage tests means I am referring to things like stuck at fault, etc. Then there is logic based. The blue one is the functional testing. So you can see that is, we don't do so much functional testing. Then this refers to logic based. These are voltage tests. And finally, there may be even other tests that I have not mentioned here. Okay. And there is an increased emphasis on what is called as online testing. What it means is, see, normally when we are using the chip, we are either testing it or we are using it. So there is a test mode. So if test mode is 1, we are testing. If the test mode is 0, it is in the normal mode. Okay. But can we have simultaneous testing? When one part of the chip is being tested, the other part can be used, things like that. So that is called online testing, and it is perhaps it makes sense when we are in the infield. That means the chip is being used. So in-field testing means testing in the field. And there is also a lot of talk about system level tests. We already talked about JTAG, right? We talked about analog test bus. So system level testing can also mean, see, individually the chip seems to work, okay, but when you make it part of a system, it may not be, it may not work, or it may not provide the right performance, right? So it may make sense to use the chip in its final context in which it's going to be used. So the reason why that has become important is, nowadays people have long life expectations. So I already mentioned to you that a car may get used for 15 years. A robot, an industrial robot also may be used for 10 to 15 years. And during testing, as I have mentioned before also, you may cause a lot of heat dissipation. So one should be aware of uh, you know how this if I am going to do in-field testing, will I create some hot spots, etc., causing aging effects and so on. Okay. So that is the reason why system level tests have to be aware of their impact. Then I think nowadays these pattern sensitive faults are coming back. Okay, mainly because of automotive, etc. See, at one time when memory tests were introduced, these pattern sensitive faults, there were a lot of papers that were published. Okay. But after some time, they all fizzled out because people said, these are all very unlikely to occur. So you are unnecessarily creating all these pattern sensitive fault testing, etc. In reality, these things don't occur. So let us stick to simple ones like coupling faults, transition faults, etc. But given that we are beginning to use automotives and functional safety is important. So there is a increased awareness of pattern sensitive faults. So these seem to be coming back. And so see, when the budget is a concern, right? See, if you have a very expensive tester to apply your scan tests and so on, then it's fine. But it may be possible for you to apply system level tests and reduce the amount of testing you do for with the tester. Okay. So it can act as a potential replacement for external testing. So that is what so in the automotives, people are very concerned about. It's a big market. That is the first thing. Okay. So as a result, it is attractive. Okay. But at the same time, um, they want, if possible, zero defects. That means their quality requirement is very high. Okay. So that is the reason why, in addition to things like scan test, including single socket fault, bridge fault, TDF, etc., they are also bringing in system level tests. Okay. And we'll talk about adaptive testing later.